Hello, this is Rick Powers coming to you from my home office for Western Technical College. And this video is about the confidence interval of the standard deviation. Now, this is based on the idea that you understand what a confidence interval is, having done it already with proportions and with the mean. And when we say what is a confidence interval, it is using an interval based on sample information, and that interval will predict where the population number is going to be. And there's all kinds of problems with saying, how does this actually work? Does it really make sense to work? And does it use the word probability? Do we have a 95% probability of it being true? And the answer is no. It's having to do with confidence. It's saying we have a certain interval and we create that based on a sample. But if we take a different sample, we're going to have a different interval, right? And so every time we take a sample, we end up with a different interval. And much of the time, 95% of the time, that interval is actually going to contain the population number. But it doesn't always. And so we say, well, we're trying this, but it's not always going to work. But it's not like the population number is somehow in there. It's the interval that's constantly shifting. So it works generally. And but what we need to do is we need to consider, how does the standard deviation work? We know that we can get bell-shaped things from a proportion if our sample size is large enough. Hopefully you understand that we can't use bell-shaped information for the mean because of the uncertainty regarding the standard deviation. We have to use the t-statistic, which is a different kind of a thing. Well, once we get into the standard deviation, then it's even more differenter. Okay, it's just strange, different. Now, in a real world situation, the only time we can use this mathematical process that we're about to describe is assuming that we have bell-shaped data in the population as a whole. And if that's not true, then this process doesn't really work. If we get an opportunity, we might be able to talk about bootstrapping, which is another method, and there are other methods for evaluating standard deviations. But basically, if you have experience with a type of data and you are pretty sure that it is bell-shaped, then you can use these methods. All right, so then what are we dealing with in this situation? I'm going to share my screen so that you can see more of what this is looking like. All right, so I'm sharing my screen and I go to this right here. What you see here is not bell-shaped. This is the distribution of the sample variance, which is the square of the standard deviation. But notice the population data over here is bell-shaped, but the sample variance is not bell-shaped. Now, what I'm going to do is I'm going to use the magic of the spreadsheet to change this bell-shaped data to look a little bit differently. I'm going to change it from a mean of 0, which is what it has right now, to a mean of 100. It's again bell-shaped here, but the variance distribution is again not bell-shaped. And now I can change the standard deviation of this. I'll make it 22 here. So again, this is bell-shaped, but this is not. So when we're talking about getting things like the variance, which is the square of the standard deviation, or the standard deviation itself, we cannot use the bell-shaped idea of what the sample is going to look like. So what do we have here? What is this thing? What is this shape that we keep coming up with that's not bell-shaped? This thing is called the chi-squared distribution. And I'm going to go back here to the actual textbook to see what this says. The critical values of the chi-square distribution. So they're doing the same process that I just did, and they come up with something which is the chi-square distribution. Notice that this is not an X. This is a chi. It's a Greek letter. It's not a chi or anything else. It's a chi, and it's chi squared. Rhymes with sky square or whatever. All right. This is the chi-square distribution. It's a Greek letter similar to mu or sigma. It's the Greek letter chi. So then, when we have this thing, this chi-square distribution, it is not going to be symmetric. It's going to change, as we see down here. There are various shapes for it, depending. But once we have a certain sample size, then the shape of the distribution will remain the same. Just as when we were talking about the t distribution, degrees of freedom causes the curve to be different. With the t distribution, it's not very different, but with the chi-squared, it's very different. Different levels of degrees of freedom create a very different shape to our distribution, and we need to use that when we talk about making this happen. Now, when we say, how do I find critical values for this thing? It's unfortunate that the textbook, as well as other textbooks, they consider the chi-square distribution always with the area to the right. And so, as you can see here, though, if we're doing a confidence interval, we don't just want areas to the right. We want areas on both ends of this. Okay. So if we wanted, for example, a 90% confidence interval, we would want 90% of the area in the middle and 5% on each side. Well, if we're looking to the right, then it's beautiful. It just works. And it's labeled then chi-squared 0.05, which is 5% to the right. But if I want 5% area to the left, unfortunately, they don't label it to the left 5%. They label it as 0.95. What that actually means is 5% to the left. Now, if you were to use a table, which I do not recommend, but if you were to use a table, this is what it would look like. These areas are all areas to the right. That's what's in the column here. And so if we had, for example, degrees of freedom 9, which would be a sample size of 10, and I'll move this up a little bit. So if I have degrees of freedom is 9, which would be a sample size of 10, and I want a 90% interval, that means 5% on both sides, here's my number for 0.05. But then if I want 5% on the other side, I can't use this 0.05. I have to go over here to the 0.95, which is over there. Now it's confusing, I recognize, but it's unfortunate tradition in statistics that chi-squared tables always refer to the area to the right of a thing. Now, if we had a 95% confidence interval, then we would have to have 95% in the middle and 2.5% on each side. So that would mean we would use this. We would be using the 0.025, 2.5% on the right, which is just where it should be, right? But then if it's 2.5% on the left, then it becomes this 0.0975 number with 9 degrees of freedom, which would be over here. And again, it's just the way that the numbers are labeled to figure out what they are. However, we don't really want to use the table now, do we? What we want to do is use StatCrunch. So if we go to StatCrunch and we go to Stat Calculators chi-square. So now if I want my 5% to the left with degrees of freedom 9, I can just hit 9 degrees of freedom and 0.05 to the left, and it just makes it happen. Well, what if I want 0.05 to the right? Well, all I have to do is change my arrow symbol and put in 0.05 to the right. And there I have it. So using StatCrunch, we're able to get these critical values directly. We don't have to look them up considering, well, 1 minus this or anything like that. That's not a consideration. Unfortunately, when the textbook asks you for what they want, they use that 1 minus alpha over 2. So you just have to make sure that you put the right things into StatCrunch based on what the textbook is asking. Pardon me. So it takes, let me make sure you have this information. If we just go with the idea of having an area in the middle of this distribution. So here's the thing, and then here is my chi-squared. It's going to look something like this. Whatever this area might be here, here's my area, okay? Then I need alpha over 2 over on this end. I need alpha over 2 over on this end. This one is labeled with alpha over 2. But this one is labeled as 1 minus alpha over 2. Because the table is always talking about areas to the right. So I hope that helps you so that you can find those critical values based on StatCrunch. If you want to use the table, certainly that's fine. But they are also there in StatCrunch. Specifically in StatCrunch, we can use the between. And if I say, oh, I want to have my 90% confidence interval, and I use the between command, it just gives it to me. So then I don't have to worry about very much. I just put my confidence amount in the probability, and then StatCrunch comes up with the critical values for the chi-squared. I just have to label them correctly. The one on the right is the alpha over 2. The one on the left is 1 minus alpha over 2. But again, as you can see, it's not actually symmetric, but it gives us the numbers that we need. All right. Feel free to let me know if you have any questions about this. And best wishes on using chi-squared.